In this video, we're going to take a look at two of the ICE table questions that are presented and make sure that we can work through them. So if you haven't done these questions, I encourage you to give them a try and then come back and take a look at them. But here it says that you've got 4 mole per liter, or 4 moles of ethane, and 2.5 moles of bromine are in a 1 liter container. So your concentration equals number of moles divided by volume. So it's going to be 4.0 moles per 1 liter and 2.50 mole per liter. So I've built an ICE table for the reaction that you can see here. And my initial concentration of ethene is 4.00 mole per liter. And my concentration for bromine is 2.50 mole per liter. And we would have none of the product at the beginning. And then it says that the concentration of ethene at equilibrium is 2.50 mole per liter. So the equilibrium is your E, so this is 2.50 mole per liter. If you've got the table now, you could pause the video and fill it in, because I'm going to do that shortly here. Okay, so now, the difference between 4.0 and 2.5 is 1.50. So you take this number subtracted from this, and it gives me 1.50 mole per liter. So the 1.50 mole per liter is the change for this reactant. The other reactant, bromine, is at a 1-to-1 ratio. So this is going to be plus 0.150, which I take from here. And then it's going to be times 1 bromine for every 1 ethene. And so it's plus it's not plus, it's minus, right? Sorry. Ooh, I'm causing a disaster here. This is going to be a minus, and this is going to be minus. So I'm subtracting 1.50, because that's what I did here. 4 minus 1.50 is 2.50. 2.50 minus 1.50 is 1.00. So that's the concentration of bromine at equilibrium. Now the product is going to be made. So it's plus 1.50 times one of these, H4Br2 is for 1 ethene. And so it's plus 1.50. So this is going to be 1.50. So I've created an ICE table and filled it in. It wants us to sketch a graph for this. And so my graph here, if this is going to be my ethene starts at 4.0. This would be, I guess, 2.0. So this would be 3.0. This will be 1.0. And I start with 4 mole per liter of ethene, and it ends at 2.5. And so it's going to get this curved line. Where it reaches equilibrium, it straightens out the curve. Then I'm going to have my bromine. Bromine starts at 2.50, and it goes down to 1.0, and it should follow the same path as the ethene. And then my product starts at 0 and ends at 1.50. And since it's a 1-to-1-to-1 ratio, the changes should be equal rate of change. So this is going to be my reaction. This is over time because it's occurring over time. And you can see that the reaction curve always starts off steeper and slows down, because as the reaction reaches equilibrium, you get less net change. Now, this also asks you to use the limiting reagent to calculate the maximum concentration of this. So with my starting amount of ethene, I can find the concentration of C2H4Br2 using that. So if I had 4.00 mole per liter of the ethene, I can make one of these for every 1 ethene. And so I would expect from ethene, I could make 4.00 mole per liter. From my bromine, I can find the concentration of Ce2H4Br2. I have 2.50 mole per liter to start off with. So if 100% of it went forward, I would get a stoichiometric amount of product made. And so for every one bromine, I get one product, so I get 2.50 mole per liter. Well, this is my max yield because I will run out of bromine before I could make the 4.0. So this is your stoic max yield. And so my limiting reagent is my bromine. The bromine is my limiting reagent. Because of that, I know the maximum possible yield and I can calculate the percent reaction. So at equilibrium, my product is 1.50. So the percent reaction is a percent yield reaction. So I get 1.50 mole per liter, but I could have had 2.50 mole per liter if 100% of it went forward. So 1.50 times, or divided by 2.50 times 100% will give me my reaction percentage. And so 1.5 divided by 2.5 times 100% is 60% forward reaction. And I know because this is greater than 50% that the products are favored. You're going to be able to do a similar kind of calculation. Here, in this case, they've actually given us some of the values. So I can see that hydrogen here starts out at 6.0 mole per liter, that my iodine started at 4.0 mole per liter, and at equilibrium, I have 2.4 mole here, and I get 0.4 mole here. So this is going to be minus 3.6 mole per liter, minus 3.6 mole per liter. If this was 0, this would be plus 3.6 mole per liter because it's being produced, but I get 2 hydrogen iodides for every one, and you could pick either of these change. So for 1 hydrogen, it'd give you the same value if you used iodine, and so it's plus 7.2. So 0 plus 7.2 is 0.72. And if I was sketching this on the curve, it'll be like that kind of a curve. So to calculate the percent reaction, I need to know how much product could be made max yield. So if this made the product, since it's a 2-to-1 ratio, it would make 12 mole per liter, right? So if I had 6.0 mole per liter of hydrogen, I get hydrogen here and I get hydrogen iodide here. I get 2-to-1, that'd be 12 mole per liter of hydrogen iodide would be produced from H2, right? So that'd be my concentration of hydrogen iodide. From my iodine, the concentration of hydrogen iodide would be 4.0 mole per liter times 2 hydrogen iodide for 1 iodine in this case, and this is 8.0 mole per liter. This is my max yield. So if 100% of the reaction went forward, that's how much I would get. My percent yield will be equal to 7.20 mole per liter divided by 8.0 mole per liter times 100%. And so I'm going to get, I think it's 90%. 90% forward reaction, so it favors the products. In the next video, we'll talk about the constant and or the equilibrium constant, and then apply it to some of these situations.